All right, thank you, and good afternoon, everybody, and welcome to our educational session for this afternoon. Hope you all enjoyed lunch, and now we're going to get down to some learning. My name is JP Cullen, and I'm the Executive Vice President and Chief Operating Officer of the Auto Fund at Saskatchewan Government Insurance, or SGI. I'm going to be your moderator for our second session today, and this session will last approximately an hour and 30 minutes. So just a quick reminder, we are recording the educational sessions and they will be available online shortly after the meeting, or the annual meeting. So today's session covers a topic that continues to shape and reshape the future of transportation: automated and connected vehicles, or AVCVs. These technologies are no longer on the horizon, they are here. They are being tested and deployed across the globe. So the question that we're posing today is Canada ready? This moderated panel will explore developments from Canada and beyond. We'll hear about global trends, research and development in this space, jurisdictional experiences, innovations from industry, and the evolving federal regulatory landscape. Most importantly, we'll be looking at the path forward, how Canada can take a coordinated and informed and safety-first approach to deploying AVCV technologies. To guide us through this conversation, we're joined by representatives from government, academia, and industry. In no particular order, we have with us today, and gentlemen, I'll just ask you to raise your hand when I call you, Dr. Christophe Czarnecki from the University of Waterloo, Colin McKay from Wabi, Dr. Peter Burns from Transport Canada, and Jerome Brito from the Ontario Ministry of Transportation. We're pleased to have each of you with us. So each panelist will start with a brief presentation to provide their perspective on the topic, where we are, where we're going, and what it will take for Canada to get there. Following their presentations, we'll conclude with a question and answer period with our guests. We kindly request that you wait until the end of the session to pose your questions. So to start this session, we're going to hear from Dr. Peter Burns. Dr. Burns manages the Human Factors and Crash Avoidance Division at Transport Canada, where he leads applied research and test method development on human factors and vehicle safety performance. With over 30 years' experience in road safety research, he has specialized in human factors, driver behavior, and vehicle safety technologies. His current research examines driver interaction with automated and driver assistance systems, driver monitoring, and the safety and usability of interface design. His work informs federal and international motor vehicle safety standards. Please welcome Dr. Burns.
Thank you for that introduction, JP. So waiting for my slides to come up. I'm going to be giving you an overview of some of our current research activities at Transport Canada related to the testing of safety and assistance systems, as well as some of the human factors research. And then I'm going to be, later in my presentation, I'll be talking a little bit about some of our policy development and regulatory development work. So next slide, please. Next. I'm going to start with a video. Yeah, here we go.
Welcome to this beautiful intersection, North Montreal and Blainville. This is a Transport Canada facility, and we're here in this mock-up intersection behind me to better study how vehicle technology can help and assist in reducing fatalities and injuries on Canadian road.
Aujourd'hui, on va faire deux types d'essais. Et là, notre véhicule doit s'arrêter. Et puis émettre également des warnings aux conducteurs.
Why we're doing this into an intersection that you will see in a city with the lamppost, with other pedestrians standing beside, is to challenge current systems.
On utilise des mannequins, évidemment, qui sont faits pour se faire
Pas des
frapper.
vrais mannequins, non, c'est ça.
On regarde aux usagers vulnérables de la route. On a les piétons, on a les cyclistes, puis plus tôt, on a vu la moto.
Pour faire les scénarios, on a beaucoup d'équipements spécialisés pour être le plus répétitif possible. Donc, dans le véhicule, on a des robots de pédale pour contrôler la vitesse du véhicule. On a des robots de conduite pour vraiment représenter le trajectoire de façon répétitive. Fait que le conducteur, lui, il est juste là pour monitorer que tout va bien, que le data rentre dans le véhicule. Mais si jamais il y a un freinage, c'est vraiment le système. Le conducteur, lui, ne va jamais toucher au frein parce qu'on veut vraiment voir comment le système réagit.
It's very important to notice that when you use your vehicle with advanced technologies, that you have limitation in the owner's manual. These limitations can be affected by the angle of the sun, if it rains, if it snows. It's not a perfect solution. It doesn't work everywhere. And this is why it's very important to understand that these features should be there as a safety measure, an extra set of eyes that will alert you and help you if there's, for example, pedestrian crossing the road where you least expect it.
Ça, c'est vraiment un test qui est représentatif de ce qu'on peut rencontrer dans une situation urbaine où il y a un enfant qui décide de traverser juste à la dernière seconde.
That's what is very interesting because it can enable us to better understand the benefit of this type of technology, how it will perform in a real-world environment while doing it safely on the test track. Il y a tellement de blessures puis de décès dans les intersections au Canada. On a la chance d'avoir une super belle équipe pour vraiment aller comprendre les limites et le fonctionnement des systèmes d'aide à la conduite.
So that gives a quick overview of some of the crash avoidance testing we're doing at our Motor Vehicle Test Center. You see, we're using very advanced equipment to assess the performance of safety and assistance systems, using steering robots, pedal robots, etc. But we can only look at a fraction of the situations that vehicles that will encounter in the real world and will need to be able to negotiate safely. So it's a real challenge to advance our track testing to address to test the safety performance of systems that perform the entire driving task across a multitude of situations. And so we're working on that, and we're also looking at simulation as a potential path forward as well. Another area of work on the human factors front is to assess the driver interaction with partial automation. So SAE level 2 systems. So these are systems that perform the driving task on highways. They maintain the speed and lane position. The thing about automation is it usually doesn't replace humans. It changes their role. So level 2 systems change the role of the driver to a supervisor. And they need, it's a very different task, supervising automation. It's not a task that they're trained for. It's very different, and it has different information needs. So we're evaluating these systems, looking at their displays and controls, measuring how user-friendly they are, how intuitive they are. And there's a lot of variability out there. A lot of these systems are different, have different capabilities and limitations. One of our concerns is mode confusion, and this is where the driver doesn't have an accurate sense of what mode of automation that is currently active. So this is a real concern, is if the automation switches off, disengages, and they're unaware of it. So effectively, nobody's driving the car. Another concern is misguided trust. We worry that people might have overconfidence in these technologies and use them in situations in which they shouldn't, or they don't trust them at all. They don't even know how to turn them on. In some cases, people don't even know these systems are on their vehicle. And in those cases, they won't benefit from the assistance that these technologies provide. Lastly, there's concerns about misuse. So with highly capable systems, there's a risk that drivers will just trust the system and say and pick up their phone and play with their phone, and that's not safe because these systems will fail at the wrong time, and the driver needs to be very attentive. The other risk is drivers may become complacent. Supervising automation is kind of boring, so we worry that it might lead to drowsiness. Next slide, please. So we're doing on-road tests of these systems, and with a checklist and experts, and we're rating these different features. We're particularly interested in how effectively these systems communicate to the driver what mode of automation is currently active and when that changes. It's really important that the driver clearly understands when there's a change in the automation and that they need to resume manual driving. We're also interested in how easy it is to activate these systems, among other things. Next. Another aspect is driver engagement. So these systems, because they need supervision, they also monitor the driver and whether or not their hands are on the wheel, whether or not their eyes are on the road in the case of some systems. And so what we do is we test how these L2 systems cope with disengagement. So we take our hands off the wheel and see what happens in time, when the warnings occur, and how they warn, and also ultimately what happens if you never put your hands back on the wheel. Does the vehicle just continue beeping at you, or is it capable of slowing down and coming to a safe stop? What we found is that the systems vary. There are very good systems on the market and others not so good. And it's a bit of concern because we're seeing some basic human factors guidance being ignored. And we've had complaints about that, complaints from drivers who said their system switched off and they didn't realize it. Next. Another topic we're doing research on is lighting for automated vehicles. Pedestrians, cyclists, and drivers require clear signals from other vehicles to interact with them safely. And that's why we have brake lights and turn signals, lights, maybe horns in some cases. It's uncertain whether automated vehicles need some additional form of communication. At the UN, there's been a proposal to have what they call automated vehicle marker lamps. So these are these cyan-colored blue-green lights that can be visible at any angle. And that basically tells other road users that this vehicle is automated. So with the University of Toronto, we did a simulation study where we exposed people to these lights in different scenarios. And they had different roles as a pedestrian, cyclist, or other driver. And we measured how they reacted. Next. Interestingly, what we found was there were 24 participants in the trial. Only one person, in the first condition, they saw the lights without any explanation. So it wasn't explained to them. And after that, we asked them, so what were those cyan lights? And only one of the 24 participants guessed right, that the vehicle was automated. And he admitted that that was purely a guess. He had no idea, maybe it was automated. The other participants thought it was some sort of new styling feature or some aftermarket modification. So these lights are not intuitive. However, everyone thought these were really important. Once it was explained to them, they felt this was essential and very important to have that sort of information about the automated vehicle status. And another reason is they preferred to be more cautious around these vehicles. They had a little less confidence. So that was an interesting result, and we'll continue to look at that. Next. So now I'm going to be talking a bit about the state of play of AV operations globally and in Canada. There is commercial deployment of level 3 systems. So this is the next step up from level 2. These systems operate on highways and they don't require driver supervision. The driver can watch a video while these systems are active. They can't sleep. They have to be available within a matter of seconds to resume the driving task. So these systems are on the market in Germany and in California. We have fleets of level 4 robo-taxis operating in, I think it's 4 cities now in the US, and Waymo, and they are deploying vehicles in Tokyo now, from what I understand. Also, there's a number of robo-taxi deployments in China. One of the main challenges, as you see, all those deployments are in Sunbelt environments. So nice sunny weather where it's very easier for the automation to function. Winter can be a challenge for these vehicles. I think it's just a matter of time before they can handle winter conditions. And industry has signaled to us that they are interested in deploying in the Canadian market in the coming years. So expect to see them in a not too distant future. Next. I think my colleagues will be touching on this too, so I'll go over this quickly. So we've had a number of on-road trials in 4 different provinces in Canada, from 20 companies, from manufacturers, developers, as well as universities. Diverse deployments looking at automated shuttles, middle mile freight, like Gatic in Toronto, as well as last mile parcel delivery. Let's go to the next slide. We get into the policy and regs side, where I'll refer to my notes. It's very important to note that Transport Canada's current regulatory framework allows the importation, manufacture, or sale of automated driving systems. So in theory, if a company wanted to sell an automated vehicle in Canada today, federal regulations would accommodate this if they can demonstrate through self-certification that the vehicle or vehicle equipment complies with existing regulations and standards. However, it would still need to be approved by the provincial and territorial road authorities for use on public roads. Recent guidance in this space includes our updated national testing guidelines for automated driving systems. That was published in 2021. Our updated safety framework, which was published earlier this year. And it provides broad overview of Transport Canada's programming to support the safe testing of connected and automated vehicles. We're currently working on an updated version of our safety assessment, which provides guidance to industry on how to develop and validate the overall safety of their automated driving systems. And all of these documents are accessible on Transport Canada's webpage. So, next. Cooperation with international partners is important to promote a globally aligned approach to road safety and vehicle regulation that leverages best practices, research, and safety expertise from the broader international community. Transport Canada is an active participant in the United Nations World Forum for the Harmonization of Vehicle Regulations. Bit of a mouthful, but that's called WP29 for short, not to be confused with WD-40. That's something very different. And in the fall of 2023, WP29 reached agreement to develop a global technical regulation, or GTR, for automated driving systems, with a targeted completion date for just a year from now, so June 2026. And Canada is co-sponsoring this GTR with 6 other jurisdictions, with the UK, Europe, US, Japan, and China, and many other countries are involved in this work. So it's anticipated when the GTR is completed, will provide the blueprint for Transport Canada to implement a Canadian motor vehicle safety standard for these systems. Next. Now, I'm going to give you a quick overview of the draft GTR. And these documents are available online, and if you can't find them, reach out to me and I can provide a link. So the requirements in the GTR are to ensure safety throughout the life of the ADS vehicle, not just from the point of manufacturer, but throughout the lifespan of that vehicle. And manufacturers need to document and implement a safety management system, which is a structured framework that considers safety through the design, development, and validation, as well as the operation of these vehicles. Another part of it is the safety case. Manufacturers have to prepare a safety case to demonstrate the system is free from unreasonable risk and it meets the requirements of the regulation and provide supporting evidence. The GTR is going to be establishing performance requirements for the evaluation of ADS driving behaviors. The safety level that they're setting must be as safe as a careful human driver, minimizing unreasonable safety risks to the occupants and other road users. There's a broad range of other requirements related to the performance of the actual driving task. Human user interaction, which is a part that I'm involved with, specifying the information needs of the users. In-service monitoring is another important part. So when these vehicles are out there, they need to be monitored to verify that they're performing safely, and there's reporting requirements on that. And there's a bunch of other elements I don't have time to get into. The cybersecurity, how data is stored from these vehicles, and how software updates are handled. Next. Yeah, thanks. So I think this is my last slide, actually. So the plan for the domestic implementation of the GTR will take a few years, and this will be done in close consultation with provinces and territories and our other key stakeholders. We'll be updating our safety assessment for automated driving systems later this fall, and the intention is this will serve as an interim tool until the GTR can be adopted as a CMVSS requirement. The implementation may also require new legislative authorities, and this is something that we're analyzing currently. And we look forward to working closely with CCMTA colleagues to advance a coordinated approach to AV regulation that ensures federal, provincial, territorial requirements operate in a cohesive fashion. Thank you.
You can all clap. Thank you very much, Dr. Burns. I'll now turn it over to Jerome Rideau. Jerome is a team lead in the Road Safety Program Development Office with Ontario's Ministry of Transportation, or MTO. He has a diverse background in public service, having previously held roles in the Ministry of the Attorney General and the Ministry of Children, Community and Social Services. In his current role at MTO, Jerome leads the development and oversight of key road safety policies and initiatives. His portfolio includes Ontario's 10-year automated vehicle pilot program, e-bikes, and measures to combat high-risk driving behaviors such as distracted driving and excessive speeding. Please welcome Jerome Rideau.
Thank you, and what a pleasure it is to be here today. So today I'm going to be talking to you about Ontario's role in automated vehicles, and there's so much to say, and I'll do my best to roll through it as we can. So we'll start with talking about why Ontario, why should testing be in Ontario, why is automated vehicles coming to Ontario a good thing, and we'll look at some of the initiatives we've taken as well as the lessons learned that could help influence the future of deployment. So currently, Ontario is already a leader in the space of automated and connected vehicles in North America. It's uniquely positioned to lead in the converging automotive and information communications technology sectors. And as you can see here in the red is the automotive manufacturing sector, where Ontario is actually the only subnational group to be home to all 5 of the top global automakers. On the right there in the blue, you'll see the information technology sector. And where that overlap is, the combination of these 2 sectors actually supports Ontario as the 2nd largest information and communications technology hub in North America. Currently, right now, there's over 300 companies exploring automated and connected vehicles in the area. And while there is a lot of opportunity, there's also a lot of subject matter expertise. Right now, there's 24 colleges and 11 universities that are providing auto-related initiatives and training. And ironically, University of Waterloo has one, and others ranging throughout that map and in other parts of Ontario. Next, we'll jump into how Ontario supports this opportunity and the subject matter expertise as a ministry. And the Ministry of Transportation has taken on multiple initiatives to support automated vehicles, but we're going to highlight 4 today, and I'm really going to dig into number 1, which is Ontario's automated vehicle pilot, which was the first pilot and testing ground for automated vehicles on public roadways in Canada, which was created in 2016. The second point, looking at economic growth, sorry if you can go back a slide. Thank you. The second, looking at economic growth, is an initiative called the Ontario Vehicle Innovation Network. That network was developed in 2021, and it provides funding and grant money towards companies looking to explore automated and connected vehicle technology, or even electric vehicle technology in the province. And to date, the ministry has funded more than $56.4 million to help support the growth of companies, some which are actually currently in our pilot today. And the third, which is playing a leadership role in coordinating across jurisdictions. Now, I'll pause here to say CCMTA has played an incredible role in this, between working groups, bringing us all here together today, and Ontario is able to support at times and look to help coordinate between levels of government and provincial ministries. And the last, looking at how are we working on connective technology and innovative intelligent transportation systems. So right now we are exploring a lot of different ones, but some that we're currently using on our highways include interactive communication boards, where the boards will give tips to drivers on if there's a collision ahead or if there is a lot of traffic, and this can help defer traffic flow to reduce traffic congestion and increase safety. Next slide, please. Perfect. So as I promised, we'll dive into the Ontario Automated Vehicle Pilot Program. And this was established in January 1st of 2016. The program allows entities such as original equipment manufacturers, technology companies, academic institutions, and even technology companies to be part of a pilot to test their technology on public roadways. These includes approvals and processes that are applications and outlined within regulation. And in order to keep pace with the technology, in 2019, Ontario introduced a few key enhancements. The first was to allow for driverless testing, which now the pilot does include, and we do have participants who are taking advantage of that part. And part of that was to add requirements and additional things, such as rules around the driverless operation, to make sure that there still remains safe. Second, we allowed for cooperative truck platooning. And for anyone who may not be familiar with this, cooperative truck platooning is a process where multiple large commercial trucks are connected and tethered together using technology and connected to primarily the first vehicle in the fleet, which is normally operated by a driver. Now, I say it's similar to a train, and it is quite cool, but it may be less cool than the steam trains outside. And the third, looking at excluding from the pilot SAE or Society of Automotive Engineers Level 3 vehicles if they are manufactured with a driving automation system and eligible for sale in Canada. Now, for anyone who may not be familiar with this technology, SAE Level 3 allows a driver to stop paying attention or stop carrying over the vehicle during a set task. And Peter touched on this a bit as well. Right now, we don't have any for sale in Canada. So it is in the US in select areas, and ultimately this framework would allow for its growth to come here. As part of our commitment to the pilot program and automated vehicles, we continue to look for best practices and research in order to make sure that we remain aligned and update the pilot as needed. And what we're going to dive into today is what has happened throughout the pilot and what have we learned over the last now 10 years coming up at the end of the year. So moving into that, we'll look at pilot participants, and we're collaborating so well that there was photos of some of them in the presentation before. So we're doing great. And ultimately, since 2016, the pilot has had 15 total participants. There are 3 active currently, which we'll dive into. The first is Gatic Inc. Now, Gatic Inc. operates, and you can see a small photo on the side there, light-duty delivery vehicles. So they are not commercial. but they do operate on a set route, and they deliver from a factory setting to a store location. So it's not direct to consumer, but more direct to the locations of the store. And then we have the University of Waterloo, who we have here today, who does a small shuttle around their campus and moves students around. And the third, interestingly, again, a different type of vehicle than the pilot, is Magna International Inc., who does a driverless small delivery vehicle. And they're the one pilot participant that is direct to consumer and also not within a set route. So they have a geofence location and area. And ultimately, a normal question is to ask, well, what about the other participants today? Well, what we found when we've engaged with them is that their testing needs have been met. And uniquely, all of their testing needs were different. Some looked to create partnerships within Ontario. Some conducted one-day testing by driving between here and Detroit. Others looked to simply come and test within weather conditions, which was touched upon earlier. So there's many reasons why, and ultimately these partnerships and building these relationships is a stepping stone to hopefully longer-term testing. So to dive in to some of the lessons learned, and really the core contribution we could probably give from the pilot so far. And next slide, please. Perfect. We'll start by looking at some of the key insights we've taken. So the stepping stones, or the things that we can take into the future to help regulate automated vehicles and this future deployment we discuss. So we'll start with identifying core requirements. And identifying core requirements is a key aspect of any program. Now, when you're working with innovative technology and new types of vehicles, these core requirements are essentially your baseline. And they are the requirements that are not flexible. So these can include things like what are the qualifications for a driver? Should they have to be licensed to meet the vehicle they're testing? What are the types of vehicles you're going to allow in your pilot? So we discussed things like different levels of Society of Automotive Engineering levels. And these baseline requirements are carried throughout exploration into new testing opportunities or deployment opportunities, and they allow for a key part of the program, which is being adaptable and flexible. So as I mentioned earlier, all three of our pilot participants have different vehicles. Now, stringent requirements that are core requirements for everyone simply don't match the uniqueness of the three different types of vehicles we have and maybe others we bring forward. So adaptability and flexibility is key for allowing innovation. And those core requirements are essentially the scaffolding that support you to be able to be adaptable and flexible. Additionally, another way to support adaptability and flexibility that we'll touch on is performance-based measures. Performance-based measures is the concept of defining the performance in which you wish to meet. So for example, the vehicle must operate safely around emergency response vehicles when their sirens are activated or coming up. And the performance-based measure allows organizations or applicants to identify how they can meet the requirement. So instead of being strict and perhaps creating red tape by saying, you must do this to prove you're safe, it allows an opportunity to collaborate and discuss how that can be met safely. And this is a big one based on the types of information too. Some have tested in the province, some have tested in the country, some have only tested in the US jurisdictions, and some are private property exclusively. So it allows for flexibility. And the last one is defining key aspects, which is very similar to identifying core requirements. But when you're defining key aspects, it's looking at some of the big questions like, what is testing? We always say testing or deployment, and we look at them, but when you sit down, what is testing? What is the difference between your testing framework and a deployment framework? What are the aspects that are going to require approval? And what are the factors that you care about, such as weather conditions or different areas of roads, that are key to you being able to identify if a testing regime would be safe? Now moving into the next one, which is encouraging collaboration. Encouraging collaboration we found to be a key driver for the success of any rollout of automated vehicles. It includes different levels of government, but it also includes collaborating even with people on the ground, such as first responders, and creating work zone plans in order to allow for individuals to know how to engage with the vehicle if they're ever in a collision or even just coming by it. What we found to date too is it's important to remember that there is a shared goal. So everyone's goal when collaborating, including the applicants, different levels of government, federal government, we want safe and successful use of automated vehicles. And ultimately where you can collaborate, you can come up with much clearer ways to be able to do that and foster public acceptance. So public acceptance, I think everyone has known since the beginning of automated vehicles, public acceptance has played a key role. It is, a lot of people love driving and going out and have the ability to, drive on their own. So really fostering that public acceptance is key. And the ways that we've seen you can do that is by being transparent where possible, allowing individuals to know when testing is coming in their area or their communities. And this will remain at the forefront, I believe, of really making sure there is success and uptake in this space. And moving into the final two here, one thing we found, and surprise, testing is expensive. It is not easy for applicants to test for long terms, and one of the ways that you can support testing long term is commercialization. So one of the things we found, and you may have noticed, is that many of our pilot participants right now serve a commercial purpose. So they give deliveries directly to consumers or for companies. And you may ask, well, why is it so important for long-term testing? And that brings us to data reporting, which is the key of the program. When we are able to establish long-term testing, we're able to identify trends, we're able to understand the technology better. And as you've seen with 3 different very unique vehicles within the pilot, there's actually a need to continue to understand. So the more vehicles we can have, the more we can encourage that uptake, and the more, to touch back on collaboration, we can meet like today and discuss our findings, share our understandings, and encourage that testing throughout the country, the more we can move towards the future. So with that, I'll leave you with a few statements to say that. Next slide, please. Ontario is a proud leader within Canada's automated vehicle landscape. And we're also a proud collaborator alongside the jurisdictions that lead in this space as well within Ontario, within Canada. We do see automated vehicles as part of our future, and we hope to be a part of that future. And testing frameworks, like the ones that other jurisdictions here have as well, are the core to that foundation, not just for Ontario, but for Canada as a whole. The data collection, the opportunities that we bring, and the testing are the core for the future to be able to be created. And we talk a lot today about, operating in other jurisdictions and taking that stuff. If I had my engineering team up here, they would tell me there is no clear transferable data for being able to test here. Having these vehicles on our roads is the way to understand if they are safe for our roads and our road safety rules. So as we continue to explore this conversation today about deployments and work through our presentations and answer questions, I'll leave you with a question as well, which is, as we continue to explore automated vehicles, as we continue to allow them within our jurisdictions, what are your personal expectations for this technology? Do you expect that it's safer than human drivers? Do you expect that it's a lot safer than human drivers? Or should the expectation be that it's nearly perfect before we explore the future ahead? Thank you.
Thank you very much, Jerome. We're now going to hear from Colin McKay. Colin leads policy and public affairs in Canada for Waabi, Canada's pioneer in applying generative AI to the physical world. Waabi's breakthrough technology, starting with autonomous trucking, will help usher in a new era of safer, more efficient, and sustainable autonomous transportation. Colin has held leadership roles in policy, public affairs, and research at Google and the Office of the Privacy Commissioner of Canada. For over 2 decades, he has worked at the intersection of transformative technologies, artificial intelligence, privacy, and transportation. Please welcome Colin McKay.
Thanks very much. I do not have a presentation. I will be piggybacking on some of the visuals that my co-panelists will be presenting after me. But I would encourage you, if you have any questions or are looking for additional data based on the comments I'm going to make right now, to just email me at cmckay@waabi.ai, cmckay@waabi.ai, and I'd be happy to reply and have a conversation. I'll start off by saying that Waabi is an autonomous trucking developer focusing on long-haul trucking using Class 8 commercial tractors and trailers. That was founded by Raquel Urtasun, a pioneer in the use of artificial intelligence and generative artificial intelligence, who is a professor at the University of Toronto and has been working in this field for over 20 years. Our headquarters, we're a Canadian company. our headquarters is in Toronto, where we do our foundational research and development as well as the software engineering for the key software and autonomous driving platform products I'm about to describe in very brief detail. We also have offices in San Francisco as well as Pittsburgh, and our main operational office and team is located just outside of Dallas, where we run autonomous trucks on the highway between Dallas and Houston every day with a safety driver. Waabi's just celebrated our 4th anniversary, which puts us at roughly half the age of other AV companies in our industry focusing on the same goals in long-haul trucking. But we are on a par to launch fully driverless operations with them this year. We've achieved that in 4 years with 2 series of financing and a very focused approach towards our technology. I think we all share the perception that over 130 years of commercial trucking, history has consistently demonstrated that human operators are inherently unsafe at scale. Human error remains the primary cause of truck-related accidents, both by trucks and by other participants on the road around the trucks. That's not to say that either drivers or trucks are absolved of any guilt or any causal factors in these incidents, but that's an observation that's proven. We feel that autonomous vehicles have the potential to reverse these trends, but it's imperative that the path to getting there is itself safe and responsible, which is a common theme across all the presentations you're hearing this afternoon. From our perspective to date, traditional autonomous vehicle systems, or as we refer to them, AV 1.0, are often reliant on complex hand-coded rules and vast amounts of real-world driving data. And they have struggled to achieve the level of safety and reliability required for widespread commercialization, as Jerome just observed as a result of their pilots and their experimentation. Commercialization is key when you're trying to develop a truly transformative technology. Waabi's approach is fundamentally different. We're focused on unlocking next generation AV 2.0 based on an end-to-end interpretable model and verifiable generative AI models. For us, when bringing AI into the physical world, we must ensure that this technology is efficient, able to generalize to the unknown, importantly, and provably safe. And provably safe is a very important distinction, especially when we're speaking about generative AI, which in the transportation context has a very different application and very different interpretations than it does in the more popular consumer conversation around generative AI. So we are leveraging the power of generative AI, we feel, in a quite hyperbolic way, but realistic, to usher in a new era of safer, more efficient, and sustainable autonomous transportation. The unpredictability of real-world driving makes it impossible to guarantee exposure to all critical, low-frequency, yet safety-critical events in the course of a physical testing program dependent on miles on the road or hours on the road. For Waabi, we consider simulation not just a great but necessary tool to achieve the goalposts of testing our autonomous driving platform against every single imaginable instance that can occur on the road. We feel that developing this next generation AV 2.0 will reduce the development time and resources needed to bring autonomy to the public roads. And it will do it in a more capital efficient way and with a much faster deployment. And that is an observation I'll have about the timeframes that we have in front of us when we're talking about autonomous vehicles and autonomous trucks in particular. That we have been taking an approach where we're focused on pilot projects and the gradual testing and evolution of the tools and the technology. The reality, whether it's the autonomous trucking industry based in North America or the autonomous vehicle industry based elsewhere in the world, that both the development and deployment is accelerating. And we're seeing accelerating market entrance as well as penetration by autonomous vehicles. For Waabi, we have 2 groundbreaking use cases, Waabi Driver and Waabi World. And Wabi World is the key concept here. It's our high-fidelity, closed-loop neural simulator that trains the Wabi Driver autonomous vehicle driving platform. It trains their Wabi Driver AI models in a virtual environment that can be manipulated from every aspect and interaction with every element within the environment. This is a simulation-first approach that can generalize to any scenario and eliminates the need for extensive, lengthy, expensive, and risky on-road testing. And I know Jerome closed an observation about needing on-the-road testing within our specific environments, with our own jurisdictions, our own communities, and I don't say that's not necessary, but operating from the assumption that there needs to be a custom testing approach and then the custom learning process before implementation within individual communities or even across sub-jurisdictions really isn't focusing on the advances in the technology nor on the potential for increases in safety on our roads. We recognize that when we're bringing AI into the physical world, we need to ensure that technology is efficient, that it's able to generalize the unknown, and it's provably safe. And we're transparent about our safe approach to developing and deploying autonomous vehicles. We share milestones publicly and continuously with regulators, consumers, the trucking industry, in order to build the public trust that's absolutely essential for public acceptance of this technology, as well as public recognition of the benefits on the roads around them, and to align all of these communities with our shared goals. Importantly, in this simulated environment, and then in the translation of the simulated environment into Wabi Driver, every decision that Wabi Driver makes is visible and traceable and explains exact reasoning behind a truck's actions in the instance that's being examined. For example, we have access to the logic behind traffic navigation, braking, lane changes, and unexpected scenario responses. And unexpected scenario responses, as we all know, is code for those things that only happen every 10,000 hours or 10,000 miles or 100 million miles that are quite consequential, but we as individual drivers will never come across them in our driving career, you would hope. Our comprehensive safety framework requires rigorous safety validation through simulator and, importantly, real-world testing. And the result, we feel, is an approach to safety that's superior to human drivers thanks to improved attention, reaction time, and additional redundancies. There's a whole separate 15 minutes conversation we can have about the benefits for the trucking industry from autonomous trucking and the pace of change that will come with the introduction of autonomous vehicles within the trucking industry that I'm happy to do off the stage, but there's some very strong arguments there as well. And as I said, at the moment, we're focused on running our trucking operations out of our dedicated trucking terminal in Dallas, running freight on the I-45 to the Houston area through our partnership with Uber Freight. And we have a safety driver in the driver's seat of our trucks, but we will be going driverless in 2025, this year. So as I said, we are on par with our competitors and developing autonomous trucking and autonomous vehicle solutions. And it's a very different use case and a very different implementation than robotaxis and autonomous vehicles in a consumer application. The difficulties are much different and the driving environment is much different, as we've discussed on this panel, both in terms of environmental conditions as well as the driving conditions around the vehicle itself. We feel that as we move towards 2030 and 2035, there will be a large-scale autonomous truck deployment and a freight network that enhances road safety, addresses the driver shortage that is bedeviling every jurisdiction in North America, and importantly, in the economic conversation we're having right now, helps strengthen the supply chain available to every industry and every consumer, not just in Canada, but across North America. So once again, since you have lots of questions, people are staring at me, cmckay@waabi.ai, and happy to follow up.
Thank you very much, Colin. I'm now pleased to introduce our last speaker, Dr. Krzysztof Czernecki. Dr. Czernecki is a professor of electrical and computer engineering and a university research chair at the University of Waterloo, where he leads the Waterloo Intelligent Systems Engineering, or WISE, laboratory, and serves as associate director of the Waterloo Center for Automotive Research, or WATCAR. You got some really cool acronyms. Dr. Czernecki's work focuses on assuring the safety of AI systems and driving behavior. He co-led the team that developed the first autonomous vehicle tested on public roads in Canada in 2018, and he has made significant contributions to automotive AI and software standards, including SAE J3164 and ISO 8800. Before joining the University of Waterloo, he worked at Daimler Chrysler Research in Germany from 1995 to 2002, advancing software development practices and technologies for enterprise, automotive, and aerospace sectors. His contributions have been recognized with numerous awards, including the Premier's Research Excellence Award, the British Computing Society's Upper Canada Award for Outstanding Contributions to the IT Industry, and numerous paper awards. Please join me in welcoming Dr. Czernecki.
All right, thank you. Thank you so much. So I normally give my presentations to a different crowd, usually scientific or engineering in AI, machine learning, robotics, and so on. But I'm so much pleased that I was invited before this audience that is really connected to the real world, has the impact, and can and will be the enabler for this future, this autonomous future. So we have to have this conversation between the engineering side, vehicle engineering side, AI automation, and the road safety community. So I'm really pleased to be here. So let's see if I can figure out this my self-driving slides. So maybe if I click, it will advance. So let's get it rolling. Perfect. So first I'd like to visualize the two most highly automated driving systems that are available in North America today, which is Waymo and Tesla FSD. These are two very different systems. So Waymo, it's actually driverless system. It's a robotaxi. I had a chance to test it myself last year in San Francisco with my son. I trusted it enough, so he was in the back, I was in the front, and we took a ride through just center of San Francisco. Pretty cool experience. Then Tesla FSD is available on private vehicles. So if you own a Tesla, you can be approved, and if you pay money for the subscription, you can have this package. It's called full self-driving, but really what it is, it's a driver assistance system, but very highly automated. So you can actually have the system drive your car with hands off. So this, in most of the other systems, level 2 systems, you actually have to have your hands on the steering wheel. So in this case, really what it is, it's a hands off, eyes on, so to speak, because you have to supervise the system. The system could make mistakes, and you ultimately responsible. It's very different than robotaxi, where there is no driver, so really you can only blame the operator or the manufacturer because there is no driver. This particular video is actually from YouTube. If you're interested, there's several comparisons where, in this case, in LA, someone actually is using Tesla FSD and had summoned Waymo taxi, which is available through an app in LA, and they enter the same destination address. And typically what happens is the Tesla FSD gets there much faster than the Waymo. That also reflects, I would say, the approach to safety. So let's say in San Francisco, my ride was, with Uber, I could have done the ride in 15 minutes. With Waymo, it was 25 minutes. Because it takes back roads and so on. It's very careful, so to speak. Okay, let's advance. So worldwide, really, what do we have? So let's focus on just the driverless system. So where there's absolutely no driver and deployed commercially. So like, let's say, robotaxi that you can, with your phone, anyone in the public can summon this thing and have a ride. So in the US, we have roughly 2,000 robotaxis in several cities in Southwest. So it's mostly California, Arizona, and Texas. In China, we have roughly a similar number, also around 2,000 robotaxis from multiple players. The big ones is it's Baidu, Pony, and WeRide. On the automated trucks side in the US, Aurora just launched a commercial operation, driverless operation, with 2 trucks. In China, we've got a fleet of 200 robo-trucks from Pony AI. So it's kind of neck to neck here, as you see, between these 2 big centers of the universe of automated driving, which is US and China. But when you think about that, you know, how big is the fleet of private vehicles and trucks in the world versus we don't even have like 10,000 of these vehicles worldwide, right? So it's really beginnings when we think about that. But we're still learning. The learning is great, of course. So I'm gonna go through a slide with a diagram, and I promise you, well, I'm a professor, I have to put up some diagram, right? So there will be only 2 slides with technical diagram, and I hope I'll make this as painless as possible for you. So I start with the classical stack. So this is really about how these systems work internally. And the point I want to make is that there's 2 fundamentally different ways of building the systems. And the first one is what's called the classical autonomous vehicle stack. So for example, this is how Waymo operates, and this is how we built our vehicle, the UW Moose, between 2016 and 2018. And it starts with sensors that sense the environment. Very often these vehicles would use cameras, just like our eyes, but it would also use laser scanner. That's great because it gives you actually a 3D distance and shape of the world. You can also see better at night because it uses infrared. And then you also use radar. So something that exists on most vehicles today with ADAS. And so these images come in, and they come in into what's called perception system. Really, that's a fancy word to say, this is the thing that interprets the input from the sensors and detects road users, whether it's pedestrian, cyclists, other vehicles, but also the structure of the world, like the map, and any other obstacles. All of that gets represented. The SIMP says symbolic, so I think of it like it creates like a drawing, like a bird's eye view map with where everyone is. And then there is another component that then predicts where everyone is going or wants to go. And then finally, there's another component that then decides what the vehicle should do, which produces the plan. And plan, really, it's the steering input, the braking input, and the throttle input into the vehicle. So essentially, this thing is a software, computer, hardware driver, electronic driver. Now, in this classical stack, the planning is really done by programmers programming rules. Think of it sort of like traffic rules, but much more detailed than that. And not just the sort of, let's say, legal rules, but also just common sense rules. How do I drive? How do I behave in different locations on the road? Then the perception part, it's in blue, it's neural networks. In fact, the only way to understand the world and create this map of the environment can be only done with AI. And since we actually have this technology over the last 15 years, that actually enabled self-driving cars. Because simply, there is no way to write a set of rules that would define, let's say, a natural concept like a human or what is a tree. It just doesn't work. And so with neural networks, you can show the neural network lots of trees, lots of humans, lots of cars, pedestrians, and other type of objects, and suddenly it starts recognizing all these patterns and is able to interpret and build this map of the environment for you, right? So fundamentally, you have to use AI. That's the point of this slide. You have to use AI for understanding an environment, for planning. Like Waymo, for example, can do this still with manual rules. Now, the point is that I put the black box there because you train these neural networks, and that behaves completely differently than these programmed rules. It's usually opaque. So it's amazing, you can train it. You know, if you move to another environment, you can give it new types of data, how maybe in that city, how roads look like. It's different maybe in Saskatchewan than, or in Regina than, let's say, Toronto and Montreal. You just collect data, and then you teach the neural network to understand and build a map for that particular city. However, it is an opaque system, and that is actually, from an engineering perspective, has been very challenging, particularly for ensuring safety. Now, the newer systems that are being explored by companies, including Wabi, is to build end-to-end systems. Now, what I'm showing here is one particular way to do that. There is this sort of, so let me define end-to-end neural network architectures. Basically means that all of these boxes, including the prediction and planning, are just trained neural networks. There is no more component where you just sit down and write rules. This is how you should behave. Everything is trained. This has advantages. It's possible to adapt to new places quicker than with rules. It turns out that vehicles that are trained that way often behave kind of more naturally in traffic. But there is a huge challenge there, which is how to assure safety of that. I should also mention that I'm on the slide it says FSD, or Full Self-Driving version 12, which was rolled out about a year ago. That's a system that's now completely end-to-end neural network. It previously used to be more like a classical stack, but for now, since for 1 year, those who are running FSD on the vehicles is just neural network driving, basically, just purely AI. But very different from Waymo. All right. Now, all of that, it's the black box that I was talking about. Okay, perfect. There is a challenge with AI, and if you have ever tried ChatGPT or a system like that, Claude or some other generative AI systems, they can do amazing things. In fact, I cannot imagine my job as an engineer, professor, programmer, and even it helps me in my sort of day-to-day life. I delegate a lot of stuff these days to some of these systems, specifically ChatGPT. Writing texts, getting advice. In the end, I have to be responsible for my decisions, but it's very useful. However, if you just read what's written there, so if you try this trick yourself, it might not work anymore because it was fixed. But I can tell you that you can do some prompt engineering and you can get something similar like that. And perhaps this is just to illustrate a point, right? So here the picture just says, the prompt says, give me an empty room with no elephant in it, absolutely no elephant, and then it draws a sort of an empty room with an elephant in it. Again, this is just to illustrate the point that these systems have certain failure modes that we don't understand. And no amount of training can assure the elimination of these faults. You can, for example, start address and improve it. And so that's why, for example, something like Waymo, they are able with AI, within a geofence, do a pretty good job, right? Now, can you do this in general, anywhere in the world, like what's sometimes called L5 systems, basically just replaces human driver and drives everywhere? Today, we don't have technology to do that. It's not possible, right? So the point is that normally in AI, what happens is AI researchers, if you go to an AI conference, they will tell you, wow, my system is 99% accurate. And in machine learning, that's amazing. Well, in safety business, this is like at least 3 or 4 nines too few, right? And remember that adding 1 9, it's like 10 times better each time. So the more nines you start adding, the more work it is, the more edge cases you have to cover. And that's the key challenge. So these two examples, these are from failures of FSD. There's lots of examples that you can find online. I'm just showing 2 specific. So the one on the left, This was demonstration from Elon Musk when he was when the FSD, the end-to-end neural network, was first released a year ago. He did a live streaming ride. I think this was in Austin, and the car just blew through a red light, and he had to intervene. And other than that, it was doing perfect job. On the right, you have an example where a person was trying to control traffic after an accident. And unfortunately, this person was hit by an oncoming vehicle with FSD enabled. And because of the sun glare, the person was not recognized. But the vehicle also didn't sort of slow down because of sun glare. There was no, there was basically reliance on the driver to intervene, but the driver didn't intervene. And that was an unfortunate accident. Perfect. Now, in the context of driverless vehicles, it's interesting that we're learning things that perhaps, as engineers like myself, we wouldn't think that this would be actually the main problem. So deployment of AVs or robotaxis, for example, in San Francisco, has shown that these vehicles, of course, yeah, they sometimes get stuck in construction zones because it's confusing, can sometimes be confusing for a human too, right? But what would happen is sometimes they would block emergency response. And there were some issues where emergency responders didn't know how to interact with vehicles. They were smashing windows or using flares, like in one of these pictures in the middle. Or they would drive, let's say, into wet concrete. Or like the right bottom, you see some interaction with new mobility devices. So these are like electric unicycles. And there's a group of these riders that actually force the vehicle, kind of mob the robotaxi to drive on the wrong side of the road. But they actually do this continuously. So the taxi was driving for like a minute or two on the wrong side of the road, right, which is not acceptable. And these are the kind of things that you really have to have some amount of deployment to actually figure out these problems. You can't do this sort of just in the lab. All right, so I'm going to just go through these challenges. So edge cases, the list is infinite by definition. I'll show you some of those. Robotic driving, so what happens is often we see that actually the second most common type of accident with AVs is other road users, like human-driven vehicles and cyclists bumping into them because they sort of stop or drive in an awkward way and others get confused and bump them. They are also hard, like with the current technology as I described, it's hard to generalize to new cities. It's getting better, but it's still, like for Waymo, it maybe took previously a year to go to a new city. Now it's maybe a few months. But it's, you have to imagine that Waymo is a very well-funded company with about $1.5 billion spent on development every year. They have 1,500 engineers. And maybe their robotaxi revenues from the 2,000 taxis will be some amount of millions, but not billions. So currently, even the business case, it's, until we have better technology that can scale faster, it's probably going to take some time. And rain is already addressed, but winter driving, it's something that the companies are working on, and I believe that's probably one of the blockers specifically for Canada, right? So that's why we don't see these things, because if you deploy fleets, you would like to do this all year and not just in summer. So I'm going to show here a few edge cases. So these are the things that you find in real-world driving. Actually, these two mattresses, they fly off. You can have a video of that. So, I have some whole collection of vehicles that transport ladders in that way, sometimes through windows. And so this is actually part of a research that we're doing. We're collecting a database of these edge cases, and we want to benchmark AI models, generative AI models, to understand them and also to perfect them to actually deal with such cases. Because I bet that none of the existing AVs has any idea of these issues, like improperly secured cargo, something that's very important within this community, right? Oh, there's a sofa that then falls off and sometimes, like if the sofa falls off, there's people who actually then hop on the sofa and hold it in place. Like I wonder, like probably a Waymo would just follow it just like a normal car, not anticipating that the sofa is going to fall down. Just to kind of summarize some of the learnings. So one important thing is that at least in the US, NHTSA, which is the counterpart of Transport Canada, but in the US, they have now a standing general order that requires all companies with level 2 systems and 3 and 4 to report crashes. And so we can learn something from that. It's a very important, the data is publicly available, so it's publicly available for researchers. As an example, from June 2021 to 2024, there's roughly 4,000 of these crashes in the database. This is sort of showing which of the companies are generating most of them. And this is not to blame any particular company. It's probably reflecting the exposure, right? So basically the amount of these systems being on the road. So if you take Tesla, for example, FSD and Autopilot, so for FSD, it's probably more than 500,000 vehicles in North America. So that's US, Canada, and Mexico. In Canada, probably 20,000 or more of FSD drivers, right, who actually drive hands-off. So we have that already here. Okay, so I'm going to summarize. I think the takeaways are, first of all, we've got a challenge here because I've told you about the very difficult technical problems of assuring AI. And we don't know how to assure this in general. You know, we can do this in geofences and in steps, but we really don't have technology that's let's say the L5 driver. It doesn't exist. And I believe that actually for that we probably still need some breakthroughs in AI. Because it's not only about the 99% accuracy, it's about 6, 7, 8 nines of assurance, right? But at the same time, we really want to bring this technology. I think there is opportunities to improve safety. There's also obviously economic benefits. And it's something that every society will have to decide on their own, right? So the approaches are different. Let's say in Europe, they usually approve things before they allow things. In North America, we have self-certification, so we usually allow things. And if things go wrong, then we ask, well, have you done the due diligence? But with what I think it's important is that the public is informed, and it's part of that conversation. Everyone is at the table, and we decide what we want to do. In order to have these decisions based on facts, scientific facts, and not just emotional kind of discussion, I think it's really important to collect data, and there should be a framework for that, right? And so it turns out that even in the US right now, it's very difficult to compare AV performance or ADAS performance with human performance. And it already starts with the fact that we often lack standardized human performance collection and data sets across jurisdictions. It's very difficult. I mean, like basically each jurisdiction will have their own ways of collecting police reports and so on. I know at least as a researcher, it's difficult to basically go to some public data set and then have access to, let's say, across multiple provinces and be able to do this type of statistical research. So in US, Waymo is doing some interesting public research with publicly available data sets. And for Tesla has been making some claims. Some of them were debunked, but it's very difficult to actually understand are these claims true or not true without having access to data. So I think that's something we really need to do both for human-driven data and for automated vehicles in future. And I think the way forward is really to collaborate among regulators, industry, nonprofits, and academia to build a shared understanding of the challenges, to learn what do we need to know, what do we need to consider, how do we strike this important balance, how do we solve this challenge. So, and I'll stop here. Thank you.